Well, hello and welcome to our first tutorial for this section. We're going to look at the first two objectives in this tutorial. We're going to be able to identify important information from a graph, lots of information there, and be able to state whether a graph is even, odd, or neither. So the section in the book where we are is section 2.2 to 2.3, and we're going to spend some time on this page right here. We've got this graph, and we'll just make this the graph of f of x, since I'm referencing f of x in most of my questions here. So here's our graph. The first, there's a bunch of stuff we can talk about. Let's first start with part A. It says to find f of negative 3. This symbol is a function notation, basically replacing x with a negative 3. So basically, I want to know what is f of x when x is negative 3. So x is negative 3, so I'm going to the x-axis to 1 to negative 3. And where is my function when x is negative 3? Oh, it's down here, right here. So what is that function value? It's right here, negative 5. So our x-axis, we all know, is right here. The y-axis has a more appropriate name, f of x axis. So we've got the x-axis and the y-axis, but the f of x is just a fancy name for y. So if I'm talking about when x is negative 3, then f of x is down here at negative 5. So negative 5 would be the answer to here. And we can ask a bunch of questions similar to this. Let's say, what is f of 2? Well, now we're just changing x to be a 2. So when x is 2, we go up to where down to wherever the function, oh, here it is, up here. The function is 5 when x is 2. So what fills in the blank here would be 5. And we've got a bunch of different ways we can ask that. Okay, so part B, I'm asking, is f of 1 positive or negative? So f of 1, very similar to the previous two questions, f of 1, now x is equal to 1, so I'm going to when the x-axis is 1, and I'm going to where the function is. Oh, I don't know exactly what value the output is here. It looks like it's maybe 4.1, 4.2. It doesn't matter because that's not the question. The question is this a positive value or a negative value? And obviously, since we're above the x-axis, this is going to be a positive value. I don't quite know exactly what it is, but I know that it's positive. Okay. Part C, it says, when does f of x equal 0? Or rather, when is my function equaling 0? Okay, well, if this is a positive, or excuse me, if this is the value of negative 5, f of negative 3 was negative 5, and this is a positive 5 up here, well, when are we equal to 0? Well, this is 5, and this is 4, and this was 4.1, and here's 3, and 2, and 1, and 0, and negative 1, and negative, wait a minute, I just crossed 0. This is when f of x is 0 on the x-axis. So when does this function actually cross the x-axis and be equal to 0? I see one right here. I know that we're equal to 0 right here. So when x is equal to negative 2, when x is equal to negative 2, that's when f of x would be equal to 0. Or we could say f of negative 2 is equal to 0. That's the function notation. So when x is negative 2, f of negative 2 would be equal to 0. Now, are we seeing any other places where this function could be equal to 0? Here's one part, and then some people are looking right here maybe. But this is not part of the function, and I know that this is not part of the function because I see a nice open dot. An open dot means that the function is not included here. If this were closed, like the other endpoint is closed, then yes, this would be another time when the function would be equal to 0. But since it's an open dot, we all know that no point exists right here on our function. So this is not another value where the function is 0. There's only one point. Okay, my next question, part D, when is f of x greater than 0? So we're talking about when is the function, another value, y, when is the output greater than 0? Well, if you think of this as sort of like an iceberg and here's the water line or something like that, we're talking about when is the iceberg above the water ultimately. And so that's what we're talking about. We're talking about this part of the function. When we're greater than 0, meaning that we're in the positive direction, we're talking about above the x-axis. Above the x-axis is right in here. So we have to describe this interval, and I would use interval notation to describe this interval. We start to get above the water right past -2, and we would be dipping back into the water if we kept going right here at 1, 2, 3, 4. So the interval is in between -2 and 4. The question is, am I using parentheses or brackets or one of each? Well, look at our symbol again. We are strictly greater than 0. I'm not interested in when we're equal to 0, so I'm not going to include the -2. I'm not interested in when we're equal to 0, and it doesn't really matter anyway because the function doesn't even exist right here at 4, so I have to use a parenthesis. But that's the interval where f of x is greater than 0. F of x is positive. Okay. Part E and F are asking for the domain and the range. I imagine we'll continue to use interval notation. You can use set notation if you want. Domain, we just reviewed in the previous tutorials. That is the set of all x's. Okay, so I like to go, of course, like I read a book from left to right. I like to look at a graph from left to right. I look at the very leftmost part of my graph, and the graph doesn't really even exist until right here. And that is the value of 1, 2, -3. The graph begins when x equals -3. And since that is a nice closed dot, I know that the output exists there, so I get to use the input of -3 and include it with a bracket. Now, I'm going to follow my graph, and I see that everything is continuous here for a while. I've got every part of my domain included. There are no jumps. There are no breaks or anything in the action. And look, we've got everything all the way up until here. This is the last value that our graph is. Actually, right before that, because this is an open dot. So it goes all the way to 1, 2, 3, 4, but it doesn't actually touch the 4. It gets close to the 4, so we're not going to include the 4. This is all of the x's that are in the domain right here in this interval. Everything from including -3 all the way to +4. What is the range? Well, this time the range, we're looking up and down. We're looking up and down the graph. So instead of looking left and right, we're looking down to up. And again, I do that as well. I go to the lowest part of the range. The lowest part of the graph that I see exists is right here at -5. And then again, I'm going to follow so I'll start at -5. And again, because it's a nice closed dot there, I get to include that range value. Okay, so I'm going all the way up, I'm going all the way up. I'm seeing how high I go up in the range, and it looks like there, oh, but then I start to come down. So this looks like the highest point of my graph. Now I don't mind that I actually have a couple double parts in the range. It doesn't matter. I've got all the stuff all the way from -5 up to here, which is +5. I'm using a bracket on that +5 because again, I have a nice closed dot. Now some people might say, well, wait a minute, 0 is not here, part of the range, but yes it is. It might not be right here, but it is filled in by this now red dot over here. So the range is everything from -5 all the way to +5. Okay, and then my final question about this graph, how many times would y equals 3 intersect f of x? Y equals 3 is a horizontal line, and y equals 3 is the line 1, 2, 3, would be this blue line right here, if I dotted that in. How many times does y equals 3 intersect our function? Well, obviously it happens twice. That's it. Happens twice. So we can tell a lot of stuff about this graph, so we spent some time on this page. We're going to look at one more thing in this tutorial, and that's the even versus the odd. So even versus odd. A function will be either even or odd, and if it's neither of those, then we call it neither. F of x is an even function if and only if, you remember this abbreviation from geometry, if and only if a point AB is an element of f of x, and if that's true, then negative a, b will also be on our function. This might be a new symbol for some people. This little e looking thing means an element of. Okay, it just basically means a point on the function, a point of the function, is in the function. It's just a symbol that means is part of the function. Okay, so an f of x is an even function if and only if you're given an ordered pair of your f of x, then if you change the x coordinate of your ordered pair, the y coordinate stays the same. So basically plus or minus a, and then the output is still b. The test for even, if you're not given the graph, you're just given the equation. The test is if you take your f of x and you replace x with the opposite of x, negative x, then you're going to get the same exact function that you started off with. That's our test for even functions. Let me give this to you visually over here. Let's just draw a graph. So we're talking about if we've got an ordered pair, let's say 2, 3, then we're saying that negative 2, 3 has to be on it for it to be even. And let's say if 1, negative 4 is on our function, then negative 1, negative 4 has to be on our function. And the graph basically has to look like a nice mirror image flipped around the y-axis. I'm just making up a graph like this. It divides exactly in the middle with the y-axis. If opposite inputs have to yield the same outputs, then it would have to fold along the y-axis. So visually, it's pretty easy to see if something is even. Okay, but if we're given an equation, we're going to need to test for it. So we're going to dump a negative x into the original and see what we get. If we get the same exact thing, then we have an even function. An odd function, f of x is an odd function if and only if, this time when we're given an ordered pair AB, and it's on our function, or part of our function, or as a piece of our function, then the opposite of A and the opposite of B has to be on our function. Okay, the test for this time, the test to see if it's an odd function, when we type in or when we plug in a negative x into our function, we get the exact opposite of the function that we originally started off with. And that's the test for an odd function. Let me show you that visually. Let's say we've got a quick little graph over here. If we're talking about odd, let's say again we've got that point 2, 3. Well, that means that we would have to have negative 2, negative 3 on our function. And let's say if 1, negative 4 is on our function, then negative 1, positive 4 has to be on our function. And you're going to see that the function will have what's called rotational symmetry, because it has to be able to rotate around on itself around this origin. So visually, an odd function will be able to rotate around itself on the origin because the opposite have to yield the opposite. So over here at I don't know, 5, 10 is a point, so negative 5, negative 10 has to be a point. So we have rotational symmetry here. Rotational symmetry around the origin, and over here we have line symmetry for an even function, and it's the y-axis. So let's look at a few examples of an equation, and I want to know if the function is even or if it's odd, or if it's neither of those, then we say that it's neither. So let's first look at the absolute value graph. The way to test to see if it's even or if it's odd, we're going to take f of x and we're going to test what f of negative x would look like. F of negative x would be taking the x that's in the absolute value bars and replacing it with negative x. But we all know that regardless of what's inside our absolute value bars are going to make this thing, this quantity, stay positive or equal to 0. So the absolute value of negative x actually still is the same thing as the absolute value of positive x. So since f of negative x yielded the same exact thing as f of positive x, then we must know that this is an even function. When we put in a negative x, nothing changed. And if nothing changes, then we have an even function. As opposed to the second one, when we're testing this guy, now this is a g of x, of course. When we're testing this, again, we type in a negative x. We put the negative x in. We're going to put the negative x in place of this and cube it, and we're going to put the negative x in place of this term. Okay. Whenever I'm substituting, I like to put it in parentheses. I didn't really need it over here because my absolute value bars were sort of my parentheses. Okay. Now let's see what happens here. Well, negative x cubed would be negative x times negative x times negative x, which does have that extra negative sign, which means that it's ultimately just negative x cubed. And here we have negative times negative x becomes a positive x. So since this is the exact opposite, I'm looking at each term. My positive x cubed turned into negative x cubed. My negative x turned into positive x. This is the exact opposite of what I needed. This is equal to the opposite of g of x. And if g of negative x equals the opposite of g of positive x, then this is an odd function. I'm not expecting that you would need to plug this into your calculator and look at it graphically. I'm expecting that you can do the test. Type in the negative x into here, or plug it in, and then see what happens to each of the terms. If the term does not change at all, then it's even. If every term changes signs, then it's odd. Let's look at h of x. Same thing, we're going to test. We're going to plug in a negative x. So negative x is going to be cubed. And, well, negative 5 is just negative 5. There's no input for this term. So let's see what happens here. Negative x times negative x times negative x, again, just simply becomes negative x cubed and then minus 5. So what happens from our original to our test? Well, the first term changes signs. It went from a positive to a negative, but the second term did not. So since part of it changed, but the other part did not, this is not even, but it also is not odd. So this is one that would be neither. Either all terms need to stay exactly the same, or all terms need to be exactly the opposite. And if that does not happen, then it's going to be a neither case. And here's our last one. So k of negative x is what we're looking for to do our test. We're going to type in a negative x, we're going to square it, and we'll do, well, plus 1. There's nothing to change the plus 1. That's just plus 1. So since this doesn't change, we know that it has to either be even or it's going to be neither. So let's see what happens with the first term. Well, this time it's negative x squared. So negative x times negative x stays positive, regardless of what x is. So we get x squared plus 1. And we can see that it's exactly the same. And since this is exactly the same, then this is equal to k of x. K of negative x and k of positive x are the same thing, so this is an even graph. Thanks for watching this tutorial, and we'll practice this more in class. I'll see you then. Thank you. All right, bye-bye.